Okay, so for this problem, our goal is to find the absolute max and minimum for this function. And remember, it is a four-step process. And the first step of the process is to find the values of the function at the endpoints of the interval. Translation, we need to find f of 0 and find f of 4 and calculate them out and see what we get. Well, f of 0 should be pretty obvious. It is just 0, since 0 cubed minus 12 times 0 is 0. For f of 4, we go to a calculator and we get, and by substituting the numbers into the function, we get the value of 16. So we have the value of our function at our two endpoints. The next things we need to do is we need to find our critical numbers, and that comes from the derivative. So f prime of x in this case is going to be 3 times x squared minus 12. This function, or I should say this derivative, is never undefined because it's polynomial, but it can be equal to 0. And we're going to set it equal to 0 and solve for x. All right, so it's going to happen at two locations. We're going to have it happening at 2 and at negative 2. Now, once you find your critical numbers, it's extremely important to make sure that we check to see that they're inside of our interval. You'll notice that 2 does fall within our interval, but negative 2 is outside. So we don't have to check negative 2 because it is outside of our interval from 0 to 4. So we need to just focus our attention on x equals 2. So step 3 of the process is to now evaluate your original function, and that's key here, at the value of 2. It's a common mistake in calculus to go back and evaluate the derivative accidentally at the number, but we know the result. That's going to be 0. So again, the idea is you go back to the original function. So it's going to be 2 cubed minus 12 times 2, which we know is going to just be 8 minus 24, which is negative 16. And then step 4 of the process is to look at the function values that we've obtained on the interval and then see which ones are going to be the absolute max and the absolute min based on a comparison. So of the values, let me go back. We've got 0, we've got positive 16, and negative 16. The smallest of those is negative 16. So we say that our function f of x has an absolute minimum at the location of 2, negative 16. And it's very important to understand that when you have an ordered pair that is a location of a minimum, this right here is the value, the absolute minimum value, and the 2 is the location of where it happens, the x value. And if we now once again look at our numbers, we have a comparison between 0 and 16. 16 is obviously the largest of those, so that's going to be our absolute maximum. So f of x has an absolute maximum or at, I should say, not of. It's another way to phrase it, but we'll keep with the at notation since that's consistent with our text. And that's going to happen again at the point 4, 16. And again, just to reiterate, the number 16, that is our value. And x equals 4 is the location of where this occurs. And again, remember, we have this absolute extreme theorem, which says that it's always going to happen for a continuous function on a closed interval. We can always get our absolute max and our absolute mins. So just to kind of recap and repeat the process, first thing you do is evaluate the function at the endpoints. Next thing we do is find the critical numbers that are inside of the interval that's specified in the problem. Step 3 is to evaluate the function at those critical numbers. And then step 4 is to compare the values we get for the original function, largest one being the absolute max, smallest being our absolute min. And that is the process for optimizing a continuous function on a closed interval.